Okay, guys, so we were busy looking at the solution to this. So when you come to the other part, I had just demonstrated that we can now have the first and the last. I took the ones in red, that is okay, right. I took this one here with this one here. And now some of you may wonder, how do you go about this? So I took this and that, but remember, we are looking for you. So definitely you has to come into play. Because if you take this and this, you could as well choose this and this. But since this was X and Y, we have U and we already have our phi B, XY, which is phi B. So this second statement here, if I call this one star, is already in terms of X and Y. So I have to bring in the U. That's why I take the red, this one and that one. And if I consider that, I end up with this equation here. So separate variables, you have linear X, this is a third linear plus C. That is direct integration of this. Now we have to merge or combine. Remember, this is one system. So since it was one PDE, we now have to combine what we have in, if I could call this one a 1, and this one we can make you the subject. We can make you the subject in this one here. Actually, you, we have now, I wish this could fit on the same page. Are they fitting? They are trying to fit. So I could take this one here. I have challenges moving. Okay, if we call this one equation 1, the one with the phi b, and then we call this one equation 2, we have to combine these. I wanted to see if I could have them on the same page. I now need to borrow and use paint, but that would be in word form now. So I have this. Guys, I also have this one here. So if you wish to call this one 1, then I also have 2. But now for 2, when I shift this, of course, this one will go away. Just remember that this one has been called equation 1. Hopefully you'll not forget that. Then we have equation 2, which equation 2 is this one here, which I'm sure you also know how we have arrived at it. We integrated here, and here we are trying to make U the subject. Since this is lean, we can express C in terms of a natural logarithm. And by doing so, you easily come up with this one here. Because if this comes this way, you have this minus this, guys. I hope we are together. You have ln X minus a third ln U. This one comes a power. So basically what you have is a ln of X minus a ln of U to the power a third. We are just playing, and this is some C. And this C can also be made. Then in here, you play with the rules of logarithms. Since it is a minus, that is X over that gives you this statement here. And of course, since it is ln of this, then we can make the subject, because you have ln of X over U to the third. This is equal to C. If you make this the subject, that's how you get X over that, e to the C. Okay. So in getting that, we now come to we come to this. Now here, this is the interesting part of the solution. Since we had the first one, this is x cubed. Of course, this one you can modify it. If you power everything to the 3, this thing just comes out. If you power the left and the right to the 3, these are just simplifications. You don't have to worry much. If you power this to the 3, and of course you power this one to the 3, then this one comes out. You get x cubed over u. This will be e to the 3c, and we are calling this one b, which is phi of a. The other one was I forget the other solution. What I know, it was a, which was phi of b. And this way, I think we had, was it x over y? If I recall, I think this was x over y, for those who remember, which was something like that. I can just quickly flip back and we have a look at it. It is right here. Yes, it is here. X over y, which is a, which is phi of b. Then for the other one, we are guys, I hope you are following. We are trying to create a link. That's why here, if this is x over y, which is a, and a is phi over b of b, the other one we are taking it to be x to the power 3 over u, which is b, and the b is phi over a. Guys, I hope we are together. So what we are generally trying to do is the constant, the constant here, which is expressed as a, but a is a phi of b. For the other part that we pick from the characteristic equation, we call this b, which is phi of a. Why? Because we have a dx over x, which is equal to a dy over y, and we have a du over u. But remember, this is what was reduced from the original PDE. So this reduction, given the fact that it emanates from the PDE, that we have as x kali u kali x and y kali u kali y, which is 3u, there must be a function that links these 3 together. I hope we are clear there, because if this is equal to this and this is equal to this, in fact, even this could be equal to another one there. We have to use that link in terms of the constants of integration that we are getting, because this constant of integration comes after integrating x alone, y alone, and in here we have x alone, but this is u. So this x here, the dx, dx over x, which is du dy, this dx links with the dx we have here over x. We can't do these two in isolation. This part usually confuses students, and I hope you will be a unique group that will not get confused. That's why I'm taking time here to make sure that I don't leave anyone behind, especially the crammers, as always. Okay, so on condition that you have, on assumption rather, that you've now understood what I'm trying to emphasize here, why I'm flipping back and forth in emphasis of why this is a and it's expressed as phi of b, but this one here is b and it is expressed as phi of a. It is to generate a link of this characteristic equation that was deduced from that. Since this is dx equal to dy, and here you have a dx over x equal to a du. The dx is a go between the first system and the second system we are solving. And that's why the constant of integration we are referring to as phi a here and phi b there is a link. It is what is working as our link between the 3 decoupled. It's what's working at the link of the decoupled system that was arrived at or derived using the Lagrange reduction method. Okay. So now when we come to this, now, this man Esau, I think he has been sleeping. Okay, so now, given what we have just said, because I've taken enough time there trying to explain that, we now introduce. Now, here you have to be a little bit careful. What you see as when we talk of for any constants, this is said could be some other arbitrary constants. Remember, when you're dealing with a PDE and you are solving over a certain given domain, for those who attended the introductory lecture last time, I told you here most of the processes you can quantify or choose to observe them as a diffusion process. And in that introduction, I think I talked more to the people doing physics, given that they have looked at this probably at length. It means because a diffusion process, it can take place in actually space. So what happens in that space? So here, when we talk of these constants here, these constants are not specific to the constants we've used here and here, guys. You must clearly distinguish that. So yes, I think I'll have to edit my notes and I pick these constants which are totally different, because what we have as A here actually could be alpha here. Is that okay? And maybe this one I could call it some totally different constant, which is maybe a beta, but not B. Why? It is because when we say for any constants, this could be alpha, we can have beta, then this one could be gamma, and this one could be what should I call this one? This one, maybe I can call, we have to use this phi, I can call this one a psi. Okay, so if they are totally different, then here we are basically saying that our psi could be a composition of alpha, gamma, alpha, gamma, and this is plus beta. So since we have these compositions, so you have that D, what we are calling the psi in the generic form. We have a dx over x. We have a dy over y. And we have a certain du over 3u. Okay, this is 3u. So we are generalizing this, but remember here, as I said earlier, you have u which is dependent on x and y. So since you are looking for a u which is dependent on x and y in this case, and you have this can be equal to that, and this can be equal to that, there would be constants of integration that you are going to deal with can be unified or can be bundled together. And here, when you talk of the bundling, remember what you are looking for is u. So if you try to make u the subject, that is the x cubed over u. That is this representation there. Then you have A, but I'm choosing to call my A, to call it alpha. So this alpha is a function of the solution we got for dx over x, dy over y. That was the x over y. I hope you remember that. We got it where? Here. That is x over y e to the c, which I call the A, and the A is phi b. Okay? We are here, yes. So plus b, and this b now is generic, not the other b, not this b. But I am generalizing this because now here we are combining what we have got for the second part of the decoupled PDE with the first part of, again, the split one using Lagrange. So it is what we are looking for, which is in terms of U. If it were possible, we would simply make U the subject. Of course, we could by multiplying by 1 over x to the 3, then it comes this way. So you have this in terms of U, which is equal to, we now generalize that in terms of the first solution, which was independent of U. That is the A into x over y. This is the solution we got when we took, this is the solution we got when we took this part here. This is this one here, the x over, and then we add a b. But this b, I insist, it is not this b. That's why I'm changing and I'm calling this alpha into x over y plus a beta there. Okay. This man, is it Albert on the what? You better ask your question. Eh? You ask, because if I now choose to unmute you, it is going to take me time, and then the noise will come through. Ask your question. You can go in the chat and you ask your question. I will come back for it if I find it there. Otherwise, I'm going to continue for now. Okay. So in this case, that is that. There are other examples that you can easily go through now. The same story. You have this PDE, which is 2 carry U carry X plus 3 carry U carry Y, which is 1. Conversion from this, which is more of a reduction or a decoupling. You have the dx over 2 plus the rather equal to the dy over 3. This is U. This will be now a du over what you have there. Same exact approach. So in this case, when I take the first and the second, I'm taking dx over 2 and du over 1. I end up with this. Then I take the first 2, which is the same as take the first 2, then you take the first and the last. Always we are looking for U, since our U is the variable that depends on X and Y. In all solutions, you always try to determine the dynamics of the dependent variable. Okay? That's why your parents worry about you, and they don't know what the future may hold for some of you because you depend on them. They know the path they have moved, and some may not even be aware of what awaits for them in the future. So in here, if you have dx over 2, which is du over 1, you solve, you integrate, you end up with this. Then you have, so this I could call this one A, which is 5b. Then I take dx over 2 and dy over 3. I do the needful, I end up with this. This could be my b, which is 5 over a. So the choice is yours. So I insist that this one here, you can call it a, which is 5 over b. And this one here, you can call it b, which is 5 over a. And then remember where we had our d, which is AC plus b, or what I had initially, I called it, I think it was SI, which was an alpha here in 2. So psi is the U, the dependent variable. Then we write alpha as a function of the 2 independent variables. That is, alpha must be in terms of X and Y. So our alpha here is what we got when we dealt with the dx over 2, dy over 3. which was 3x minus 2y, which is this one here. So the A here is what I am calling the alpha, then plus beta. Right. Then you do all the others. There are more examples in here that you can go and play with. All of these are for you. I need to activate. You go play with all of these ones. They are yours. There is nothing much there. All of these ones, you can go and you play with them. Same story, same approach. Okay, we are going to look at something a little bit different here now. Let's look at something a little bit different. Quite related, but the approach is a little bit embedded in what we have just discussed. So here what we have some initial conditions. Okay. Oh, there is something in the chat. I'm not getting the solution. Okay. No, whatever. But is it that the general solution is not unique because we have different options for the choice to make? No, it is unique, Mr. Noareva. The choice is, the solution is actually unique, though what we are dealing with is a kind of indefinite given that we don't know those constants. But you remember when you did your linear algebra, you had those parameterized systems. And if you remember those parameterized systems, you'd have a certain P here. Maybe this is a 1, a 3, a 4, and then you do have maybe plus, and sometimes, by the way, what you have, this would be, sometimes we define, maybe this is P, but there is a certain X here. Maybe this is a half X or 2X plus 3, then you have another one here, which is Q. And then you have something in, and you know that for the different values of P and Q, this system would be sensitive to those changes. So the same applies here. Since we don't have, this is, it's not initialized, we have no initial conditions. For each value of alpha and beta, or for each value of A and B, you will actually get a solution that is unique to those choices that you have made. It's not that it's not unique, no. Okay, these people want me to go into their specific challenges. Okay, let's continue now, guys. So we are looking at let's look at an example with some initial conditions. Okay, we can first of all try to generalize. So this is directly related to what we have just done. So what is this? I have this and I can write it in terms of the characteristic equation, but please be mindful that in here you have you have Kali U, Kali Y, you have Kali U, Kali X. Is that okay? And since we have a U here, it means this one can go the other side. I hope I'm with you guys here. Okay, let's first of all try to do the conversion. If you use a Lagrange, what would this reduce to? There is a coefficient of 1 here. Here we have that coefficient. This one is this way, we can take it to the other side. So if we remove this and we take it to the other side, it means, guys, please don't get lost. I have Kali U, Kali Y plus this plus that. So if I'm to take this one on the other side, it means this one goes away here. Where is my black? This one goes away. So it becomes equal to minus U. I think you follow me there. So if it becomes equal to a minus U, what would this imply? That would imply that we have a dy over 1. This is a dy over 1. I hope we are together. This one over 1. Then we have a dx over that one. This is equal to a dx. Hopefully we are together. And this dx is over u plus y. This is u plus y. And then this is equal to, remember, it was plus u. The u crosses the equal sign, it becomes minus u. So it becomes the variable we are looking for, that is the du over u. This becomes du, but negative, guys. Errors a little bit. Okay, this becomes a negative d. This one should go away. A negative du over u. Hopefully I'm clear. I hope I'm clear now. What is a little bit unique here is with respect to the examples we've looked at, you'll find that these first two are strictly in terms of x and y. Of course, for those who have been following. This one would be a certain dy over something here, maybe y, dx over something here, and this one. But this time here, we have a dx which is over a u plus y. And now there we have to be a little bit careful. Okay, so how are we selecting these? I hope you guys are following. I will guess that the silence is a sign that you are really following. Okay. So what do we have? Now, from what we have in red here, if I choose a different color, okay. So if we now take the red here, rather the blue there with the blue there. If I choose to take those two there, I think you can see here, if I take this and this, definitely I get this one here. That is the blue you see here. Hopefully no one is getting lost. So I have my du over u. This negative crosses the other side. So that's why I have du over u, which is minus dy. Okay. So since I have this, then I can also take, I hope we are still together. Then I can also take the first and the second. And I'll take that one now in black. If I take the first and the second, this one now here. If I take the first and the second, I have a dx over u plus y, which is equal to a dy, which is this one here. I am confident that no one is getting lost. Okay, now that that is said, we can look at the condition. What I'm going to look at, I hope we are clear there, guys. Now we have to look at the condition. What does the condition say? So we have a condition here. Remember, this is dependent on x and y. So what is the condition? We are saying that if you initialize at y0, u of x0 is 0. I hope we are together. So the solution we are going to get, when we substitute y0, that will be x. But remember, when we do this substitution, remember once we say, remember we have a u which is a function of x and y. Is that okay? This must give us something. So if it gives us something, now we are saying whatever that something is, if we substitute a y, with a 0, if the y becomes a 0, if y takes on that 0, we are saying it will become x. So if it becomes x, what is this new u? Since we have initialized, because this is one of the initial conditions, so we have only initialized at x equal to 0. And you remember, usually we denote by 0. Yes, there is a x, but y has been initialized at 0. we can say that term there, we can just call it a certain u of 0, and we denote it with this epsilon, because one of this is initialized. You could even initialize x and you leave y fixed. So that is the condition we are throwing somewhere here. If you see, I am distinguishing it with a red. So, but remember, this is for only y going to 0. So if you get it, when we substitute, which I'm going to demonstrate shortly, if we say that generalized, yes, you remember even in the is 1, you have a certain population, which is with respect to t, and this is some exponential term here. You have e to maybe a certain, we can call it, this is x. We can just unify that one. Maybe there is a certain lambda x. Then you say at n0, when you try to throw in the t here at t0, you say, okay, n0 will be my n naught, n subscript 0 here. And then you end up with a certain n naught, then e to the maybe lambda x. These are the things you're doing in the biomath, you guys. So you say, if I initialize for this particular value here, then I know that my original population before anything had perturbed that system in terms of emerging diseases and all other would be assumptions incorporated into your system. We would say the undisturbed or unperturbed system is the n0. So here we are saying if it is u, which is a function of x and y, we are initializing only the y. So we are saying for that system, for that solution, we'll have got for x0, this will be x. But if we have this and we know that for that 0 is that, then it means we can find the value of epsilon in terms of what is given here as x. So maybe to clarify this more, we can go through our example here. I hope I've not lost any one of you guys. Now, given what I have just explained here, let's go through this. So I have broken it down, the red, rather the blue and the black, after converting this using the Lagrange approach, and we ended up with a red here. I took red, blue and blue. I have this one here. Then I took the entire black, which is this black here. I have been explaining the U0, which is epsilon, which is this red here. Now let's try to work through the solution. Okay, so we first of all solve the one in blue. Guys, let's solve the blue. So when you solve the blue, where is, okay, so, and I'm going to solve using the blue. So I'm looking for the color blue. Please pay attention. By the way, are you here? Can you guys hear me? Can I see some yeses in the chat before I start solving this? Are you hearing me? Are you with me, guys? Okay, good, 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 good. You can stop at that. At least I know I have participants. I thought you had disappeared. Okay, so let's continue. So I am saying now, if you look at the blue, I'm now solving the blue. Of course, you are going to separate variables here. So on the left, you are going to get ln u. On the left of blue, you will get ln u. This is equal to what? Ln u, this is a dy. This will give you, when you integrate this one, you will simply get a y here, a minus y, plus a constant of integration, of course. So this will be minus y if you integrate, plus a certain constant of integration. Guys, I hope we are together. So you have a certain y plus a certain constant of integration. Now, what do we do? What we are doing here now, we are making u the subject. When you make u the subject, this is equal to your e, which is minus, this is y plus c. I hope we are together. So if I take this one, this is of course, I don't have to really dig into the details of this. You guys know what is happening. That is e to the y, and I have e to the c. So the e to the c is some form of constant. I guess we are together. So if e to the c is some form of constant, what do we have now? So what I have is a u. I hope we are together. But guys, please be mindful that our u, I hope we are together, which brings us back to this red here. Given that this is in terms of u and y only, the u I am getting here is in terms of y alone. There is no x. And remember here, it is the y that is going to 0. I hope you are following me. The x and y with the 0 is x here. U of x, y, but y is 0 is x. I am talking about this one here. But this u of 0, which we are taking to epsilon, it is now the one I am talking about here, first of all, because what I have is in terms of y only. So I have a certain u, which is a function of y alone. This is equal to what? I have this e to the c. I can call this e to the c. I am calling this one a certain constant. I can call this one a certain a. I hope we are together. So if I call this one a, it means I have a, then this is e to the power minus y. Hopefully we are together, guys. Okay, now I throw in the 0. Remember, according to this condition here, I hope you are following me. I am looking at this condition, guys. According to this condition here, this one in light green, this condition here, we are saying y is 0. But remember, even here, I am taking y 0. That's why I'm saying, since here we are initializing at y 0, I can have a certain y 0 now. U in terms of y alone, which will give me a certain eta. Because this one cannot be independent of that substitution there. So it means now that if I go back to blue, I have less than 1 minute. I need to finish this small part here. So what I'll get now, it will be my u. This is a 0. Remember, y is 0. This will give me a certain a. Of course, e to the 0, this is a 1. But I am calling this y, u0, I am calling it eta. So eta is equal to a. So it means if I come back to substitute into this one here, I have my u as a function of now, u which is equal to, this is y, but now after substituting it is both of those. Here it is now x and y, because we know u depends on both. This will be a, which is eta. Then this is e to the minus y. And this one here is exactly what we have there. These two are these ones. I hope we are together there. But remember, when you're substituting into this, the original, after we have substituted, now the u we are taking back into it is u, which is x, comma y. I hope we are together. Because now my population at that. So I have this epsilon, and I have now to find this epsilon. So we are going to deal with this, and we remove this epsilon. So